Hello guys, welcome back to my channel. Today we're gonna discuss the first three problems of the Codeforces round 1068. So yeah, let's go. The first problem: sleeping through classes. You have n classes today which are numbered from 1 to n. The classes are described by a binary string s of length n. We call a class I important if and only if si equals 1. For each important class, you must stay awake and listen to it. You are very tired and wish to sleep through as many classes as possible. However, falling asleep takes time. If you listen to an important class I, then you cannot fall asleep for the next classes. That is, you must also stay awake in classes I plus 1 to I plus k. For classes that are not important, you may sleep through them unless the rule above forces you to stay awake. The task is to find the maximum number of classes you can sleep through today. Okay. So the main crux of the problem is that we are given a binary string. 1 means that class is important. If si equals 1, that means ith class is important, and we must stay awake for the important classes. Again, then you are very tired and you want to sleep through as many classes as possible. But since it is given in the problem that if you stay awake on class I, then you cannot fall asleep for the next k classes, so you have to stay awake uh, from I plus 1 all the way up to I plus k. Okay, now you have to calculate the maximum number of classes you can sleep. So this is just a basic implementation problem. There's nothing too much uh, complexity, so we'll understand it like this. So let's say so my bad. So let's say we have a 0 0 0 1 0 0 1 0 0 0 1, something like that, and let's say k equals 2. So this is a free and we have a count which tells us the maximum number the number of classes that we have skipped. So you see, this is a free class, so we can skip this right now. This is a free class, again we can skip this. This is a free class, again we can skip this. Right now we are here, and we know this is an important class since this is 1. And so if this is an important class, I have to keep a variable, maintain a variable, let's say, where I'll assign it to the last important class. So the indices are as follows. I'm writing down the indices, and now the last is 3. Since this is an important class and we cannot sleep through it, right? It is given in the problem. Now we are at 0. We can increment the count only if we have to stay awake on the important classes, and then we cannot fall asleep for the next k classes. So if we attend this, we have to attend this important class, and then for the next 2 classes we cannot fall asleep. So for the 4th and the 5th class we cannot fall asleep. So I'll just check if this is I, by the way. So if I minus last, which is the position of the um, important class, so this is 4 minus 3. If this is greater than k, then I can attend, otherwise I cannot. So 4 minus 3 is 1. That means I'll have to stay awake. So now I'll move here. Now 5 minus 3 is 2. And then I have to stay awake for 2 consecutive for 2 classes if I attend this. So I cannot take this 5 as well. And so I'll move here. But since this is 1, right? So what we'll do is we'll update the last variable to 6, and then we'll go here. We'll check if 7 minus 6 is greater than k. It is 1. It is not. So we'll move here. Is 8 minus 6 greater than k? No. So if I attend first class, I cannot attend. If I attend this one, then I'll have to stay awake for 7 and 8 because k is 2, right? If k was 1, then I'll only have to stay awake for the 7th class. So now 7th and 8th we cannot attend, and then we can go to 9th, and 9 minus 6 is 3, which is strictly greater than 3, so I'll increment the count 4, and then we'll go here, we'll update the count, the last to 10, and then this would be over. So we can sleep for the 4 consecutive or 4 classes, right? So this is our final answer. This was just an implementation problem. Also, one more thing that you could have done would be that as soon as you encounter a 1, you know, increment the your loop or the ith pointer by k, but since k could be large, like something like 5, and then if you jump over let's say some this by this distance 1 2 3 4 5, then it might happen that you may encounter some ones in between, so you'll have to handle this. But otherwise I think this is a nice sweet approach. So yeah, that's pretty much it for the first problem. This is the code for this one. I'm initializing the last by -1, since if I encounter any leading zeros like this, so I do not have any restriction right now, because since I haven't encountered any important classes, so I can just pick these up, right? So I'm just checking if si equals to 1, that means it is an important class, so I'll just mark last as I. Otherwise, if last equals to -1, then I can just increment the total, or if I minus last is greater than k, then also I can increment the total, and then at last I'll just get the total. So that yeah, that's it. Now we'll move to the second one. So yeah, this is the second one. Niko is playing a game. Her score is denoted by an integer k, which is 0 initially. The game has n turns. On the ith turn, Niko is given a red card with an integer ai on it, as well as a blue card with an integer bi on it. She must choose exactly one of the cards and update her score according to her choice. If she chooses the red card, her score becomes k minus ai, where k is the score before the turn. Okay. If she chooses the blue card, her score becomes bi minus k, where k is her score before the turn, right? After this, the game proceeds to the next turn, or ends if it is the nth turn, right? Your task is to find the maximum possible score Niko can obtain at the end of the game. Okay. So basically, we have been given two arrays, A and B, and k is 0 initially, and we need to, for every I, that is because we need to perform n, where it is given, the game has n turns, so we have to perform n, or we have to play the game for n turns. For the ith turn, the Niko can either choose ai, so then the score would become k minus ai, or she can choose bi, and now the score would become bi minus k. And at last, we need to find what is the maximum possible value of k, right? So let me just take this example. The first thing that I was thinking in this contest was db, because I could either pick the ai or bi, and every I generated two possibilities. So since n was very large, this we cannot brute force this, that is try all possibilities, so we'll have to think of something else. So this is I0, I1 and I2. This is the array A, this is the array B. So first type of operation is where new k, I'll call that k dash equals to k minus ai, and the second operation is where k dash equals to I think it's bi minus k, right? Yeah. So these are two types of operation that she can perform on this array. So you might think that a greedy approach that would work. Let's try to do it by greedy. So k is 0 initially. For now, k is 0. So if I perform the first operation, this would be 0 minus 4 would be minus 4. or if I perform the second operation, that would be bi minus k, which is minus 3 minus 0. So we can make this a minus 3 since minus 3 is greater than minus 4. And now we are here. Now k is minus 3. So we can either perform the first operation, that is minus 3 plus 8, which is 5. So if we perform the first operation, k was minus 3 minus ai minus ai, so ai was minus 8. This would have been a 5. Or I could perform the second operation, where bi would be minus 7 minus, and k was minus 3. So this had became something like minus 4, I guess. So this was minus 4. So I could take a 5. So I'll update this with a 5. And now again we have two options. Either I could do a k this 5 minus ai, which is minus 1, so this becomes 6. Or I could perform bi, which is 0 minus k which was 5, so this is minus 5. So this is greater, so I could choose this one, and this becomes 6. But this greedy approach will not always give the right answers, because if you'll see carefully, the second operation is kind of special. Why am I calling this special? It is because we have a minus k here, right? So this is the previous k, okay? So if this is the previous k, I can see that if I had something like let's say I had something like maybe 1000 and maybe 10. So you, according to your greedy, you might if you perform the first operation, you'll get a minus 1000 here, because k is 0, so 0 minus 1000 is minus 1000. If you perform the second operation, you will get a 10. So according to a greedy thing, you'll take this one. But the thing is, if you had a 0 and a 0 here, or anything else, you can actually revert this. So after performing this the first operation, you can, when you go on this index, then what you can do is perform the second operation, and now this becomes 0 minus, and k was b was 0, right? So 0 minus, and k was minus 1000, so minus 1000. So this became 1000, which is the maximum. So you'll see that greedy fails here, right? So that is one thing. The most important thing, I'll just bring this down. Okay, I'll just write it separately itself. So the first operation was k dash equals to k minus ai. The second operation was k dash equals to bi minus k. So I'm saying that this second operation is kind of special, because this inverts the state that k is in. If it is a negative integer, then it just reverts it, and this becomes k becomes positive. Otherwise, if k is positive, then this reverts it, and this becomes k becomes negative, and then it adds a bi to it. So these are the only two options that we can have, and I'm claiming that with each iteration I only need a maximum or a minimum element, right? I only need a maximum and a minimum. Why am I saying that? So to prove that, let's say I have two variables. Let's call them kmax and a kmin, and then this was the k for I minus 1 iteration. Now we are on I, so we have 4 choices. Either do a kmax minus ai, or a kmin minus ai, or do a bi minus kmax, or do a bi minus kmin. Okay, so these are the only four options that we have. If we perform the first operation on both kmax and kmin, so we'll get these two things respectively. Similarly, if we perform the second operation on both kmax and kmin, we'll get these two, right? So I'm saying that can you figure out that which of the two terms are maximum and minimum? So if you'll see carefully, this terms this term and this term would be maximum, since this is kmax and we are just taking ai out from it, and this is k minimum, which is the minimum k, and then we're taking that from bi, we are subtracting that from bi. If we subtract kmax, then this term would actually be the very this term actually would be very big and will decrease the overall sum. So these two will contribute to maximum. Similarly, kmin minus ai and bi minus kmax, these two will contribute to the minimum. So this would be something like, if I take k dash max equals to max of k max minus ai comma bi minus kmin. So this is a new k new k, and similarly kmin would be minimum of bi minus kmax and kmin minus ai. So these would give us the new k maximum and a new k minimum, and now k max would be equal to this new k maximum, and then k minimum would be equals to this new k dash minimum, right? So that is essentially it for the problem. But for the intuition, uh, why we are always keeping track of only maximum and minimum? So I'll draw a number line here so that it is easier for you to see. So if I draw a number line like this, right, and if I have some points here, let's say this is 0, so there are some points like these. So I'm saying that this is minimum and this is maximum, and these are all the points in between. So I'm saying that this is if this is maximum, this is minimum. So I'm saying that these maximum and minimum elements will only change the answer by the maximum possible value, right? Because we are essentially performing either the first operation, this one, or we are essentially performing the second operation. So if we perform both of these operations on k max, and we perform both of these operations on k min like we did this, so we can then see that taking the max out of k max minus ai and bi minus k min, because this is the maximum or this is the minimum possible k, and this is the maximum possible k. So don't you guys agree that this will only give me the new maximum k, and this is what the global minimum and of k, and this is what the global maximum of k. So if I subtract the global maximum of k from bi, and if I subtract ai from global minimum, don't you guys agree that this will give me the global minimum, because I'm subtracting a very big term here, that is global maximum of the array, or global maximum k, and I'm subtracting ai from a global minimum k, right? So essentially these points become kind of useless. If you'll see, these points have no real value, because why would I want to go in between? Why do I want to pick these elements when I can just pick a more minimum one and a more maximum one? Why would I want to pick this? Just tell me that. So if this is let's say 10, this is a 5, then why do you want to pick a 5 here? Why do you want to pick a 5 here if you can pick a 10? That will make it more minimum and that will make it more maximum, right? So indeed, if you'll see this carefully, if you'll just observe this number line carefully, then you'll understand that we only need the extreme corner points of the array that are boundary points, the minimum and the maximum point. We do not need anything except that. So these and this and actually this and this point are actually responsible for constructing the final answer, and then we can at last just take the maximum of k max and k minimum. Since the maximum is always maximum, so we'll just return this. So we can at last just print k max, and that is pretty much it, right? So the main intuition for this problem was that you realize that we only need the minimum and a maximum point. We do not need anything in between, because if we, let's say, needed this one, then k minimum would be this point. Let's say this is -10 and this is a -5. So you just think for a second that for which case would it be beneficial to take -5, because if I'm taking this and if I'm taking this and this, so I want this value to be as minimum as possible. So I'll take a -10 here so that it becomes more negative, because these two are contributing to the minimum element, right? And this has to be as large as possible, or as minimum as possible as well. So instead of taking a -5, I'll always take a -10. So a more negative element or a more smaller element will contribute heavily for this, or a more negative element or more smaller element will actually make this whole thing larger, right? That is why for each iteration I only did a maximum and a minimum, and that is pretty much it for this problem. So this is the code. I'm taking the maximum out of R1 and B1, which is k pos denotes the maximum and k neg denotes the minimum, and then I'm just doing that, taking the maximum minimum, and then I'm just outputting the maximum. I can just output a k pos here as well. So this is pretty much it. Now on to the next problem. I hope you got it. We'll move to the third one. Okay. So in this is Kanade's perfect multiples. In the afterlife school, Kanade studies a peculiar number game. Okay. She gives you two integers n and k, as well as an array A consisting of n integers, where one is less than ai is less than k holds. For integer b, this is a set, something like set, where bi is also between 1 and k. We call it complete if and only if both of the following condition holds. So for each I from 1 to n, at least one divisor of ai is contained in b, and for each j from m, all positive multiples of bj which are less than or equal to k appear in the array at least once. You have to find a complete set B with minimum possible size, or determine that no such set exists. Okay, so I need to find a complete set B with the minimum size. So essentially what is given in the problem, we have been given an n and a k and a integer array A. The values of A varies from 1 to k, and then I need to construct a set B or an array B where every element of B, let's say every element of B has every multiple of, let's say, any element of B is contained in set A. So I'll just write it down so it is easier to see. So let's say if my set B was 2, 3 and let's say maybe 7 or a 5 maybe. So I'm saying that if k is 30 or not 30, maybe, yeah, let's do a 30. So I'm saying this question is saying that for all positive multiples of bj which are less than or equals to k appear in the array at least once. So this is the set B. We're actually will think of this in the reverse order. If we have set B and we'll construct a set A from this, let's say. So this is the set B, and this is the problem is saying that all positive multiples of Bj which are less than or equal to k appear in the array A at least once. So all positive multiples of 2 from 2 to 30 must appear in set A. So I'm saying that 2, 4, 6, 8 up to 30 exist in the array A, right? Similarly for this one, I'm saying that from 3 to all the way up to 30, all its multiple exist in this set A. And then similarly for 5, all the way up to 30, all the integers exist in the array. That is what I'm saying. And then if that is so, then we can print this set, and this has to be the minimum possible. So I'll just take a sample case, then it will be much easier to see. So 3, 2, 4, 6 and a 6. So this is 3, 2, 4 and 6, right? And k equals to 6. I'll just sort this array, so this is much more easier to see. So this is 2, 3, 4, 6, and these two conditions are essentially the same, this one and this one, right? So this says that at least one divisor of ai is contained in B. So this is ai, right? So they are saying that at least one divisor of ai, divisor means all the element or all the element that divides this number. So the divisors of 2 are 1 and 2. Similarly, divisors of 3 are 1 and 3, since these are prime numbers, right? The divisors of 4 are 1 to 4. So any divisor of this number, any divisor has to appear in set B. This is true for all the elements, right? So now if you see 2, 4, 6, these 4 and 6 are nothing but the multiples of 2, right? So don't you guys agree that if k equals to 6 and this and let's think about this way, if we are in on a 2, right, then I'm saying that from 2 all the way up to 6, all of its multiple should be should appear in array A. From 2 all the way up to 6, all the multiples of 2 should appear in array A, right? So for example, if 4 wasn't so for example, if there was no 4 here, so this array would have become something like 2, 3 and a 6. And now if I'm on the 2, I can see that I need to take let's think about this from the set B perspective. So I set B, all the elements or any element in the set B or how do I explain this? Let's say if I have a 2, then I'm saying that this 2 is the least possible multiple that is there in set A, and then I'll take this element and then I'll take its multiple. So this is 2, I'll take its multiple, which is 4 and a 6. So if 2 is to be there in set B, then don't you guys agree that all of its multiple are also have to be present in set A, right? This is set A, and if 2 is to be there in set B, then I'm saying that all of its multiple from 2 all the way up to 6, so 2, 4, 6 has to be there in A. But since 4 is not present, we cannot have this 2 in the set A, right? Now this is done, we cannot have this 2 for 2 in set B, right? But the question says every element of a array A some divisor of that element has to be present in set A, no set B, sorry. So I'm saying that 2 cannot be a valid candidate. Let's call it a candidate valid candidate, because 4 is not present. So the question says that at least one divisor has to be there. So the divisors of 2 are 1 and 2. So 2 cannot be a valid candidate. Let's check for 1. So if 1 has to be there in set B, then all of its multiples up to k has to be present in set A. So multiples of 1 up to 6 are 1 2 3 4 5 6. That is what is there in the problem, right? For each j, all positive multiples of bj which are less than or equals to k appear in the array at least once. So that is what I'm saying. If 1 has to be there, then you know all the numbers from 1 to 6 have to be present in array. But since they are not present, because 1 is not there, then 4 is not there, 5 is not there, so this becomes this also becomes not a valid candidate. And then this is not possible for 2. No matter what we do, this is not possible for 2, right? So that is the main observation. So if it is not possible for 2, this just contradicts our statement right here, because it has to be possible for all the elements. So we'll print a -1 in this case, because it is not possible. It is given in the problem, if no complete set B exists, print a -1. So we'll print a -1, right? Now let's take our original array, which is 2 3 4 6. So this is our array A, 2 3 4 6. And then you guys agree that in the problem it is given every element of set A, some divisor of that element has to be present in set B for every element. So 2 has divisor 1 and 2, 3 has divisor 1 and 3, 4 has divisor 1 to 4, 6 has divisor 1 2 3 6. So I'm starting from 2. So if I have to take a 2 in the set B, if I have to take a 2 in set B, then all of its multiples up to 6 or up to k has to be present in set A or in array A. So multiples of 2 up to k are 2 4 6, right? And we can see that 2 4 6 are present. So 2 is a valid candidate. I can say that 2 is a valid candidate, because 2 is a divisor of itself, right? And the multiples of 2 are 2 4 6. So if I take a 2 in the set B, all of its multiple all the way from 2 all the way up to k are present in this set A. So I can keep this in set A, and then I can go to 3. Now essentially if I have to add a 3 in this set B, then I'm saying that all the multiples of 3 all the way up to k has to be present in set in the array A, right? So multiples of 3 up to k are 3 and 6, and we can see that 3 and 6 are present. So we can add a 3 to this set also, right? Now we are on 4. The divisors of 4 are 1 to 4. Now let's not go into 1 and 2. Let's just consider 4. So if we have to take a 4, if I have to take a 4 in this case, then don't you guys agree that I'll need all the multiples of 4 all the from 4 all the way up to k. So this is 4 only, because the next multiple is 8, which is greater than 6, so we'll not include that. So 4 has to be there in the array, which is there. So we can include a 4, but we will not include a 4. Why? Because we need to minimize the set the length of the set B, right? So if I were to include this 4, this will only increase the size of set B, since we included a 2 which is a divisor of 4. So this the first condition holds true, that for every element in AI, some divisor of it has to be present in set B. So if I were to remove this 4, then also this condition holds true, since 2 is a divisor of 4 and 2 is already contained in this set. and now we go to 6. Similarly for 6 also, 2 is a valid divisor, and then we have already added a 2 in this case, so we'll not add a 6, and then this gets terminated, and this is our final answer. And so you'll see this is our final answer. So this is basically it. First of all, I need to sort the array in order to become in order to iterate from the least possible element to the greatest element. So another case would be something like 3 4 9 6 maybe. Then we actually, if you're thinking that we need to generate all the divisors of any element, then you're wrong, because we do not actually have to generate all the divisors. We can actually do that in root n, but we actually do not need that. It will anyways result in TLE, since n is up to 2e5. But anyways, I'm saying that I do not have to generate all the divisors and then check for every divisor. Basically what approach might be coming to your mind will be that we can find all the divisors of all the elements. We can keep that in a set, and then we can check for all the divisors, that every for any divisor all its multiples up to k are present in the set A. Then we'll add that divisor into our final array, and then we can just print. We can do something like that. If you're thinking, then you would be wrong, because that would result into a time complexity of n root AI, or max of AI, I would say. So AI is up to 1e9, so this would be 1e10, which will result into a TLE. So I'm saying we can actually eliminate that thing, and then I can say that if let's say 1 and 2 are divisors of 2, then we can claim that we actually do not need to think about this one, because this 1 is actually lesser than 2, right? And so if it is lesser than 2, then if I were to take this one, then the problem says that all of its multiple up to k have to be present in the array. But since 1 is lesser than 2 and it is not present in array A, if it is not present in the array A, that would mean that it fails for the first one, for the first multiple itself. Let's say if I have a 4, so the multiples of, or the divisors of 4 are 1 to 4. So if I had a 4 and an 8 and k equals to 4 or k equals to 8 in this case, so you guys can see that we actually do not need to worry about 1 and 2, because we're sorting the array, and then this is the least possible element which is possible. If I were to take a 1 or a 2, they do not actually exist in this array, right? This is the array. They actually do not exist in this array. So if they do not exist, so if we take this element and then we check for this, then this will obviously fail, no? Because there are multiples of 2 are what? 2, 2a, or this would be 2, 4, 6, 8, or the multiples would be represented in the form of 2x. So 2 itself is not present, no? So this condition will fail, because a set A has to contain every positive multiple of 2 up to k. So that would be 2, 4, 6, 8. Even if 6 were present here, this will still fail, because 2 itself is not present, right? So I'm saying that I actually do not need to worry about all the divisors of any element. We can just take this element, and then we can see that what are the multiples of this that exist in array A. So I'll take this case, which will make it much more clearer. So 3, 4, 6, 9. 3 has a divisor of 1 and a 3, and so we cannot take a 1 or anything lesser than 3, because that is not present in the array. If it was present, then we could have just taken that first, right? So we can just eliminate this, we can think about 3. So if let's say k was 9, right? If k was 9, then we can start from 3 and see the multiples of 3 up to 9, which are 3, 6, 9, all of which are present in the array. So 3 is a valid candidate, so I'll just add this to a set B, right? Since every multiple of this is contained in set A. Now about 4. 4 is not a valid candidate because multiples of 4, the divisors of 4 are 1, 2 and 4. We do not need to worry about 1, 2, since if um, we had to take 1, 2, they had to occur in this set A, right? Otherwise, why do we have to waste time on taking 1, 2, right? So we'll not think about taking this 1, 2. We'll think about taking this 4, and then we'll write down the multiples of 4 all the way up to k, which are 4 and 8. And since 8 is not present, 4 is only present. This is not a valid case. For 9, we can see that the divisors of 9 are worth 9. 3 we have already taken, we'll not take this. Since multiples of divisors of 6 are 1, 2, 3, 6, we have already taken a 3, we'll not take this. This is our final answer, since we need to minimize the length of B. So I'm saying that we can always begin from the least possible element. We can check for all its multiples in the set A, and then if all of its multiple exist in the set A up to k, or obviously, then I can say that this is a valid candidate, and let's add this to our answer. Also, we'll remember all of its multiple, so that we do not start any other iteration for 9 or 6 for its corresponding multiples, because that will only increase the size of set B. We do not actually need to increase the size of set B, because if we had a 3, 6, 9, you can see that if 3 is a valid candidate, if k was 9, if 3 is a valid candidate, then you might we can claim that 6 is also a valid candidate, because all the multiples of 6 are a multiple of 3 as well, right? So we can see that if 3 is a valid candidate, then 6 is also a valid candidate, and since 6 is a valid candidate, 9 is also a valid candidate, right? Because every multiple of 9 is a multiple of 3. So we can see that we do not actually need to include this and this again and again. We can just start from the lowest possible one. We can see that the multiple of 3 are 6 and 9. So do not just remember them and do not include them again when we encounter them, and just add 3 to our final set, and then keep doing this for all the elements. And this is probably just it for this problem. I hope it makes sense, by the way. I was actually very confused on how to explain that to you guys, but I hope it makes sense. Also, the time complexity, if you might think, is n square. It is not, because this is a harmonic series, which results into a time complexity of n log n. Because let's say I have an array something like 1, 2, 3, 4, 5, 6. Then I'm iterating of on all the multiples of 1 up to k, then all the multiples of 2 up to k, all the multiples of 3 up to k, for in the n. So this is n by 1 plus n by 2 plus n by 3 up to n by n, whatever, and then n we can take common. This is 1 by 2, 1 by 3, something like that. And then this is a harmonic expression, and the time complexity of this is n log n, right? So this is essentially it for the problem. I hope you got it, though I'm actually very confused if you would have gotten it. I think I kind of did a not so great job in explaining this problem, but if you have any doubts, you can try to solve this one by yourself. Just to give you a recap, I'm saying that I'll sort this array first, and then I'll start from the very first element. I'll start from the very first element itself. I cannot take all of its divisors which are lesser than the number itself, because if it were to occur, then I would have just started from that one, and then this would have been covered by the lower divisor. But since that divisor is not present, that means this will not be a valid candidate, because it is not in the array, right? So I'll just start from the number itself, and then I'll mark all the multiples of this as visited or in a set, so that I do not include them again, because I'm saying that if 2 is a valid candidate, then all of its multiples are also a valid candidate. Since the multiples of 2, let's say the multiples of 4 and the multiples of 6 are also multiple of 2, right? So we do not have to include them again and again. So I'll just add them to our set, and then we'll continue this for the next element. 3 is not seen. Now we'll add a 3 to the set. We'll check if all the multiples of 3 are present in the set A. All the multiples up to k obviously are present in the set A. If yes, then we'll add this to our set B, and then we'll keep doing this, and this is it. So this is the code for this problem. This is the code. I'm sorry. So I'm taking the input, forming a map of frequencies, because I need to find that every element every multiple exists in O of 1. And then I sort this array and I create a answer vector. Then I start iterating from the first element. I check that it is not present in the set which is already seen before. If it is not, then I start iterating over all its multiple. I check if these exist in the array A. If they do not, then I can just print a -1, because I cannot this is not a valid candidate, and every element has to be a valid candidate, right? So we can just print a -1. Otherwise we can insert that into the scene set, that the scene set will actually remember the elements which we have already seen, and then we can push this AI to our final answer, this AI, right? That would be outside of this loop, and then we can keep doing this for all the multiples or all the elements in the array. And then if this condition is never executed, that is every element is a valid candidate, then we can just print the size of this set, and then we can print all the elements of this set, right? I hope you got this condition, by the way, that even if one multiple of it does not exist, if let's say I had a 3 and a 9, and k would have been a 9, then the multiples of 3 up to 9 are 3, 6, 9. So I cannot take a since the divisors of 3 are 1 and 3, I cannot take 3. This we have seen. I cannot take a 1, I'll have to take a 3. So in order to take a 3, 3, 6, 9, that are multiples of 3 all the way up to k, have to exist in set A. But 6 actually does not exist in set A. That is what I'm saying. So if it does not exist in set A, then we'll print a -1. Otherwise we can just insert this into the set, and then we're good. And this is it. So these are the first 3 problems of the Codeforces round 1068. This is the longest video on my channel by far. I hope you guys got it. I hope you guys enjoyed it. Today is also the Lead Code weekly contest, so I hope I'll make a video on that one as well. But yeah, see you guys in the next one.